Hello everyone, I am Cabuñas. I am a civil engineer and I am also teaching engineering subjects, and we have the second part on the discussion of moment distribution method. So if you missed to watch the first part of this discussion, I have posted the link of that video in the description below. In this second part, we are going to solve a second example. But if you think you'd like to learn the principles regarding moment distribution method, so I would suggest to watch the first part of this discussion. Now we have the second example. We have this overhang continuous beam. As what you can see, we have the overhang member of this beam. We have CD. Okay, so in which we can compute the moment at that point C from the side C to D by using equilibrium equation. But in this case, we will try to use moment distribution method to compute the rest of the internal or the member end moments. So first we compute for the fixed end moment. So we have fixed end moment AB is, of course, this is equal to 0 because we do not have a load on the span of AB. Okay, and FEMBA as well is equal to 0. But for fixed end moment BC, we have here WL squared over 12. Okay? In which if we have this type of loading, our fixed end moment on both supports is WL squared over 12. But on the left support, this is counterclockwise. That means we have positive moment. And for the right support, we have a clockwise moment. That means we have negative magnitude. So this is a W. We have 10 times 9 squared over 12. So we have 67.5 kilonewton meter. This is positive. For a fixed end moment CB, we have negative 67.5 kilonewton meter. But for CD, we can now compute MCD by just cutting at this point, then applying equilibrium, correct? That means we have 4 times 30, that is the moment at that point. This is 120 kilonewton meter. And the rotation of our moment CD is counterclockwise. That means we have positive at that point. And then we compute for the stiffness. We have stiffness of member AB. We have 4 EI over L. We know that EI is constant, so we can just eliminate EI because that would be cancelled eventually. So we have 4 EI over L is 6. That means we have 2/3. Okay, 2/3 EI. For KBA, we still have a 2/3 EI. Correct? For KBC, we have 4 EI over 9. KCB is a 4 over 9 EI as well. And now, since we have already computed moment CD, actually we can eliminate CD on our analysis. But since we eliminate the overhang here, that means our ruler support is converted to a exterior ruler support. So that means we have to apply the alternative approach because this is applicable to this type of problem, because again our ruler here became our exterior ruler support. So meaning we multiplied 3/4 to the stiffness index BC. Okay? So therefore our KBC here must be multiplied by 3/4, and that we have the modified value of BC, which is 1/3. Okay? So again, we can now compute the distribution factor, and we know that at the fixed support, we have a 0 because we have no rotation at point A. But on the side of BA, we have the distribution factor of BA is equal to the stiffness BA over the stiffness BA plus the stiffness BC. So we have here 2/3 EI over 2/3 EI plus 1/3 EI, but we can cancel EI here, so that means we have 2/3. Now for distribution factor for BC, we have KBC over KBA plus KBC is equal to 1/3 over 2/3 plus 1/3. This is equal to 1/3. Okay, so we have now the distribution factors. So we have the distribution factor for BA, which is 2/3. For BC, we have 1/3. Now for C, we have 1, again because we eliminate the overhang and we set the ruler here as an exterior support. Okay, and then we have the fixed end moment. We have AB is 0, fixed end moment for BA is 0, fixed end moment for BC is 67.5. Okay, the fixed end moment for CB is negative 67.5, and the moment for CD is 120 kilonewton meter. Okay, so we have now these moments. So we can now start the analysis by multiplying the fixed end moment to the distribution factor, but again we take note the negative value of the distribution factor. So we have a 0 times 0, of course we have here 0. Then on point B, since we have two fixed end moments, so we have a 0 plus 67.5. Of course, that would give us 67.5. Then multiply it to negative 2/3. That is for the side BA. So we have here negative 45. Then if you multiply 67.5 to 1/3, or that is negative 1/3, that would give us negative 22.5. Okay, now on this side we have to add negative 67.5 and 120, so we have 52.5. Then multiply it to negative 1, that of course would give us negative 52.5. But since we eliminate the overhang side here, so we only have the left point or the left side of C as being included in our analysis. Okay, so therefore we stop at 120 on the right side of C. So in this case, we can carry over the moment. So again, this is our first analysis. So we carry over the moment, then divide it by 2. So we have negative 45 divided by 2. So that means we have negative 22.5 here. And we have a 0 divided by 2. Of course, we have a 0. Now, on this side, we have negative 52.5 divided by 2. So we have negative 26.25. And since we are using here the alternative approach, so at the exterior support, we end during the first cycle. So we cannot carry over negative 22.5 moment to the support C. So again, we stop at this point. So this is locked, but we still have to continue the analysis on the point A and point B. So in this case, we can multiply negative 22.5 to the distribution factors. We have here 0. Then we add 0 and negative 26.25. So it would give us negative 26.25, right? Then multiply it to negative distribution factors. So we have negative 26.25 times negative 2/3, that would give us positive 17.5. Okay? On the other side, we have negative 26.25 times negative 1/3, that would give us 8.75. Okay? So again, to compute for the unbalanced moment, so we multiply the carryover moment times the negative distribution factor. So we have carryover moment, the sum, we have negative 26.25 times negative 2/3. That is 17.5. But on the other side, we have negative 26.25 times negative 1/3. That would give us 8.75. So this is our second cycle. So we carry over the moment, then divide it by 2. So we have 17.5 divided by 2. So we have here 8.75, but we still have here 0. But since we do not have a moment that can be carried over to the right side of point B, so that means we can stop at this point. So we have a 0. So multiply 8.75 to its distribution factor. So we have here 0, and the remaining here are now 0. So we can stop our analysis at the third cycle because all the values here come 0. So therefore, we can now add all the values from 0 to 8.75, and that would give us negative 13.75. And since we have negative sign, so our moment AB is equal to negative 13.75 kilonewton meter, or the rotation is clockwise. So we have clockwise rotation. Now on the side of BA, so we add from 0 to 0. So we have negative 27.5. So our moment BA is negative 27.5 kilonewton meter. So the rotation is clockwise as well because we have negative sign. On the side of BC, so we add, so we have 67.5 minus 22.5 minus 26.25 plus 8.75. That would give us MBC equals to 27.5 kilonewton meter, and the rotation is of course counterclockwise. The same value with BA but opposite in direction because again this is in equilibrium. Okay? Now at point C, we add negative 67.5 and negative 52.5. That would give us negative 120. And this is the moment CB. So you have negative 120 kilonewton meter, and the rotation here, since we have negative, that means we have clockwise rotation. And on the side of CD, so by using equilibrium equation, so we have here 120 kilonewton meter as well. So we have MCD is equal to 120 kilonewton meter, and the rotation is counterclockwise. So the same value with CB but opposite in direction. That means they are in equilibrium. So these are now the member and moments of question or example number 2. Okay? Now for our example number 3, we have this continuous beam ABCD in which A and D here are fixed supports and EI is constant. So we can first compute for the fixed end moment. So we have a fixed end moment AB. This is a triangular load. So that means going back to our fixed end moment formula, on this side of our triangular load in which the highest point or the highest magnitude, we have WL squared over 20, but at the point where we have a 0 magnitude, our fixed end moment there is WL squared over 30. So that means at AB, we have WL squared over 30. So we have W is 27. That is the magnitude of the highest or the height of our triangle. L is 6 squared over 30. That means we have 32.4 kilonewton meters. And the rotation is, since our assumption on the left side is counterclockwise, that means this is positive. Okay? But on the right support, we have a fixed end moment BA in which the highest point is located or the highest magnitude. So we have WL squared over 20 as the formula to be used. So therefore, we have 27 times L is 6 squared over 20. So we have 48.6 kilonewton meter, and since the rotation on the right side is clockwise, that means we assume that as negative. And then for a fixed end moment on the side of BC, we have WL squared over 12, and this equals to W is 27, L is 6 squared over 12. This would give us 81 kilonewton meters. That is positive because the rotation is counterclockwise. Fixed end moment CB is equal to that is negative 81 kilonewton meter. So we have the same value but opposite in direction. Now, lastly, we have fixed end moment of CD. We have WL squared over 20 because that is the location of the highest magnitude of our triangular load. So that means we have here 27 times 6 squared over 20. That is negative 48.6. That is positive 48.6 kilonewton meter because that is counterclockwise in direction. And lastly, we have FEMDC. We have WL squared over 30, and we have already computed that one. This is the same with AB but opposite in direction. We have negative 32.4 kilonewton meter. So we have now these fixed end moments for all supports. And then we compute for the distribution factor by first computing for the member stiffness. So we have the distribution factor AB, in which our support A is a fixed support. That means we have DF equals to 0. Okay? But for DFBA, we still have to compute for KBA because we use this formula, KBA over KBA plus KBC. Okay, so our KBA here is equal to 4EI over L, and that is 4EI. Our EI here is constant. That means we have the same flexural rigidity all throughout the continuous beam. Over L here is 6. That means we have 2EI over 3. KBC is equal to, that's still the same, 4EI over 6. That means we have 2/3 EI. So for our DFBA, we have 2/3. We can eliminate EI because that would be cancelled out eventually. So we have 2/3 plus KBC 2/3. So that would give us 1/2. Okay. And for DFBC, we have KBC over KBA plus KBC. This would give us 2/3 over 2/3 plus 2/3. That means we have 1/2 as well. And lastly, for DFCB, okay, so we have KCB over KCB plus KCD. But first, we need to compute for KCB, which is we still have 6 meter length. So that means we still have a 2/3 EI. And the same as with KCD, in which we still have a 6 meter length as well. That means we have a 2/3 EI as the member stiffness. So that means our DFCB here is 1/2, and DFDC is equal to 0 because this is a fixed support. Okay, so we have now these distribution factors for all supports. So we have the distribution factors. We have a 0 for AB, 0.5 for BA, and 0.5 for BC, and 0.5 for CB, and 0.5 for CD as well, and 0 for DC. In this case, we can now write the fixed end moment. So we have for AB, we have 32.4. For BA, we have negative 48.6. For BC, we have positive 81. And CB, we have negative 81. For CD, we have here positive 48.6 and negative 32.4 at DC. So we can now use the traditional or the general method. Again, the alternative approach can only be applied if we have hinge or ruler supports on the farthest point of our beam. Okay? But in this case, we have two supports at both ends, so that means we will be using the general method. So the second step here is multiply the fixed end moment to the negative distribution factor. So we have 32.4 times 0. So we have here 0. Then at point B, you add these two moment, so we have negative 48.6 plus 81, we have 32.4. Then 32.4 multiplied by negative 0.5, we have here negative 16.2. And on the other side, BC, we have still here negative 16.2 because we have the same distribution factor as BA. Okay? Now, on the side of CB, so we add 81 and 48.6. This would give us negative 32.4, correct? So multiply 2.5, that would give us positive 16.2 and positive 16.2 on the side of CD. In this case, we have negative 32.4 times 0, then we have here 0. So this is our first cycle. For our second cycle, so we carry over the moment negative 16.2 on point A, and then we divide it by 2. So we have negative 16.2 divided it by 2. So we have negative 8.1, correct? And then 0 here. On this side, we have positive 8.1. In this side, we have negative 8.1 if we divide it by 2. Now on this side, we have a 0, and we have here positive 8.1. And then we compute for the unbalanced moment. So we multiply the moment to its distribution factor, but we have to include negative to our distribution factor. So we have 0. You sum up 0 plus 8.1. This would give us 8.1 multiplied by 0.5, negative 0.5 to be specific. So we have negative 4.05 and negative 4.05 on the other side as well. Now in this case, we have 8.1, correct? So we multiply 2.5. Now in this case, we have negative 8.1. Then if we multiply it to negative 0.5, this would give us 4.05 and 4.05 on this side as well. And then we have here 8.1 times 0, so this would give us 0. So this is our second cycle. Now for our third cycle, same procedure. We carry over the moment. So we have negative 2.025. Here we have a 0. We have 2.025 here. We have negative 2.025 on the side of CB. We have here 0, and we have here positive 2.025. And then we multiply to negative distribution factor. We have a 0 here. So if we add these two, we have a 2.025, and then we multiply to negative 0.5. This would give us negative 1.0125 and negative 1.0125 on this side. Then on this case, we have the sum is at negative 2.025, and if you multiply it to negative 0.5, the result would be 1.0125. That's positive. Okay, and the same as on the other side. And here we have 0. For our fourth cycle, we carry over the moment. We divide by 2. So we have negative 0.506. Here we have a 0. In this case, if we divide by 2, we have positive 0.506. But in this side, we have negative 0.506. We have here 0. And then we have here positive 0.506. And then we multiply to its distribution factor. So we have here 0. We add these two. We have 0.506. And then we multiply it to negative 0.5. So we have negative 0.253 for both sides. On this side, if we add these two, we would have negative 0.506. If we multiply it to negative 0.5, we have positive 0.253 for all points, for all sides. Again, because we have the same distribution factor. And in this part, we have a 0. So this is now our fourth cycle. For our fifth cycle, we carry over the moment again. We divide this one by 2. So we have negative 0.127. Then we have here 0. We have this side positive 0.127. We have here negative 0.127. We have here 0. And at this point, we have 0.127. That's positive. So we multiply to distribution factor, we have here 0. If we add this 2, we have positive 0.127, but if we multiply it to negative 0.5, we have 0.063. We have here 0.063. On this side, if we add this 2, we have negative 0.127. So if we multiply 0.127 to negative distribution factors, we have here negative 0.063 for all sides, because they have the same distribution factor for BA and BC. Now in this case, we have negative 0.127 plus 0, we have negative 0.127. And if you multiply it to negative 0.5, that would give us positive 0.063. And in this case, we also have 0.063. And then we have a 0 on the end. Now for our 6th cycle, we stop when we have a 0 decimal places. But in this case, we can actually end, but I guess the unbalanced moment is quite too large pa for me, but this is your preference. But I would suggest that you end when we have 0 on the decimal place. Now on this case, we can carry over the moment. So we have negative 0.060 divided by 2. We have here negative 0.032. We have here 0. We have here positive 0.032. If you divide it by 2, on this side we have negative 0.032. Then we have here 0, and we have here 0.032. So we multiply to distribution factor. Here we have 0. If you add this 2, we have 0.032. Then multiply to the distribution factor. For each side, we have negative 0.016 and negative 0.016 as well. So in this case, we have positive 0.016 and 0.016 on this side, and then we have a 0 here. And then we carry over the moment. So we have here 0.008. Okay, this is negative. We have here 0. We have here 0.008. If we divide by 2, then we have here negative 0.008. We have here 0, and we have here 0.008. And then lastly, we have to multiply to the distribution factor. We have here 0. Then if you add these 2, we would have 0.008. Then multiply it to negative 0.05. We have negative 0.004 for all sides. And on this point, we have positive 0.0004 for all sides. And at this point, we have 0. But since we have now values which is approximately equal to 0, then we can end here. So therefore, we can end our analysis during the 7th cycle. Because again, our unbalanced moment here are approximately equal to 0. And these are too small that we can consider this as negligible values. So we can add all the values from the 1st cycle to 7th cycle. So we have 21.57. This is positive. Now this is now our moment AB. But since this one is positive, therefore the rotation is counterclockwise. Now on BA, so we add from the 1st to the 7th cycle, we have negative 70.1949. That means this is our moment BA, and the rotation is, since that is negative, so therefore we have a clockwise rotation. Okay, so these are our, on the BC side, we have 70.2031. As what you can see, we have slight error. This might be because of round off error. So this is our member moment BC, and the rotation is counterclockwise because we have positive value. Now on the side of CB, we have 70.2031. This is negative, so that means our moment CB rotates clockwise. Okay? Now on the side of CD, we have the moment 70.2074, and this is our member end moment CD, and the rotation here is counterclockwise. And lastly, for member DC, we have negative 21.602, and since this is negative, so our moment DC is in clockwise direction. Okay, so as what you can see, we have the same, almost the same answer. Siguro the reason why we have a slight error is because of how we round off the decimal, and approximately they are equal. And since we have a symmetrical structure, so this is obvious that all the values here are the same in magnitude but just opposite in direction. Okay? And that ends our example number 3 and the second part of this discussion. Now on the third part, we will try to apply moment distribution method in the analysis of frame structures. If you wish to continue my discussion regarding MDM, just look for the link of the third part in the description below. Thank you guys for listening, but please don't forget to subscribe and hit the notification bell for more videos. Thank you guys, and see you on my next video.